Now we'll discuss our regular languages. First, we'll have the knowledge of regular expressions, regular languages, and equivalence between languages accepted by FA and regular languages, and its closure properties. First, we'll study regular expressions over the set of alphabets sigma. Phi is a regular expression, and epsilon is also a regular expression. And for any alphabet in sigma, A is a regular expression. There is any symbol in sigma, that is a regular expression. If R1 and R2 are regular expressions, then R1 plus R2 is a regular expression, and R1 concatenated to R2 is also a regular expression. And then R1 star is a regular expression. And nothing else is a regular expression. Phi is a regular language corresponding to the regular expression phi. This set epsilon is a regular language corresponding to the regular expression epsilon. For any symbol A in sigma, the set A is a regular language corresponding to the regular expression A. If L1 and L2 are regular languages corresponding to the regular expression R1 and R2, then L1 union L2, L1 concatenated to L2, and L1 star are regular languages corresponding to L1 plus L2, corresponding to R1 plus R2, R1 concatenated to R2, and R1 star. For example, if epsilon is having the symbol 0, 1 and alpha is an element of sigma star, such that alpha does not contain the symbols 1, then it is 0 star. If alpha is an element of sigma star and alpha contains only the symbols 1, then it is 1 concatenated to 1 star, which can be doubled by, that is 1 plus. And the sigma star is nothing but it is 0 plus 1 over star, but 0 star plus 1 star is not equal to 0 plus 1 star. If alpha belongs to sigma star and alpha contains only zeros or only ones, then it is denoted by your 0 0 star plus 1 1 star. If sigma is 0 1, having the elements 0 1, the parenthesis is a regular expression, can be omitted when the order of evaluation is clear. For concatenation, the dot can be omitted, that is for r dot r dot r dot r is denoted by rn, that's 10 times of r. And 0 plus 1 over star is not equal to 0 plus 1 star, and 0 star plus 1 star is equals to 0 star plus 1 star, that is parenthesis can be omitted in regular expressions. That sigma has the symbol 0 1 and alpha existing in sigma, then which contains odd number of ones, then it is equal to by 0, 1 0 star, 1 0 star star and 1 0 star. If alpha is a string in continuous symbols 0 1 and sigma, so any two zeros in alpha are separated by 3 ones. That is 1 star, 0 1 1 star, 0 1 star and 0 and 1 star. Alpha belongs to sigma star. Alpha is a binary number divisible by 4. Then divided by 0 plus 1 star and 0 0. And if alpha is a string which does not contain 1 1, then it is 0 star 1 0 plus outer star and 1 plus epsilon, or 0 plus 1 0 star with 1 plus epsilon. If R is a regular expression, the regular language corresponding to the regular expression R is denoted by L of R. We'll study some rules for language operations. If R and S, R, S and T are languages over 0, 1, then R plus phi is equal to phi plus R is equal to R. R plus S is equal to S plus R. R concatenated to epsilon is equal to epsilon concatenated to R is equal to R. R concatenated to phi concatenated to R is phi, which is also a regular language. And R concatenated to S plus T is equal to R concatenated to S and R concatenated to T. The R plus is equals to R star. We'll rewrite rules for regular expressions. If R, S and T are less than 0 1, then phi star is equal to epsilon and epsilon star is equal to epsilon. R plus epsilon plus H R star. R star is equal to R star plus R plus epsilon is equal to R star, R star, R star, star. So these are the rules how to rewrite the regular expressions in different forms. Now we'll go to the closure properties of the class of regular languages. Theorem: the class of regular language is closed under union, concatenation and knee closure or knee star. If L1 and we'll have to prove, for that we'll take L1 and L2 to be two regular languages over epsilon or sigma, sorry. Then there are regular expressions R1 and R2 corresponding to L1 and L2. By the definition of regular expression and regular languages, R1 plus R2, R1 concatenated to R2 and R1 star are regular expressions corresponding to L1 union L2, L1 concatenated to and L1 star. The class of regular languages is closed under union, concatenation and knee closure or knee star. Now let's study equivalence of language accepted by finite automation and regular languages. To show that the languages accepted by finite automation and regular languages are equivalent, we need to prove for any regular language L, there exists an finite automation M such that L is equals to L of M. And for any finite automation M, we will have L of M is a regular language. For any regular language L, there exists in finite automation M such that L is equal to L of M. The proof is given here. First we'll take let L be a regular language, then there exists a regular expression R corresponding to L, so that we can construct an NFM from the regular expression R1 such that L is equal to L of M. For this we will have a basis if R is equal to epsilon. So M is given like this as in figure. The starting state with epsilon transition will have the final state. If R is equal to 5, so M is given by a starting state only, no transition will be there. If R is equals to the set A, where A is a symbol in sigma, then M is given by the figure where the starting state and a final state with the transition connected with the transition E. So induction hypothesis, how to prove? We'll have induction hypothesis. Let R1 and R2 be two regular expressions with less than n operations, and there are NFS M1 and M2 accepting regular languages corresponding to L of R1 and L of R2. And we'll go to the induction step. Let R be a regular expression with n operations. Then we construct an NFA accepting L of R. Now R can be in the form of either R1 plus R2 or R1 concatenated to R2 or R1 star. For regular expressions R1 and R2 with less than n operations. Now if R is equal to R1 plus R2, then M is shown in the figure. We are having for R1 starting from S1 to F4 ending with F1. For R2 we are having starting from S2 to ending with F2, and both are connected through a starting state at S with two transitions. Both are epsilon, that is null transitions. If R is equal to R1 concatenated to R2, then M is like this. For R1, the starting state is S1 and final is F1. For R2, the starting state is S1, S2 and final state is F2. And to R1 and R2 are connected by a transition, there is null transition epsilon. If R is R1 star, then M is given by this figure, where R1 is S1 connected to S2, S1 connected to F1, and for the star or knee closure we are having another starting state S and final state F, and the starting state S and final state F are connected through the epsilon transitions as given in the figure, so that we will have the loop for star, that is R1 star. So therefore from the above inductions we can prove there is an NF accepting LR for any regular expression R. Now we have some examples. So 0 star is given like this, 1 0 plus is given by this figure, 1 0 plus star is given by this, 1 is given by this, epsilon is given by this, and 1 plus epsilon is given by this figure. Now can this be, if we are connecting all the pictures as given in the graph or figure, can these two states be merged? The answer will be no, because they cannot be merged. So be careful when you decide to merge some states. For any finite vector mesh name, LM is regular language. Proof is given here. You want to take a finite vector mesh M with Q, sigma delta Q1 and F. The Q is number of states Qi, where I lies between 0 to 2 or 1 to n, that is 1 less than equal to I less than equal to n for some positive integer n, and let R of ijk be the set of all strings in the tribe M for some state Qi to state Qj while passing through any state Ql for L less than equal to k, and I and j can be any states as given in the figure. Now if R of ij 0, we'll find the transition A from Qi to Qj. R of ij 0, we'll find A plus epsilon if I not equal to j. You'll find R of ijk, so R of ijk minus 1 plus R of I k minus 1 and R of k minus 1 star R of kj k minus 1. We'll find the figure like this. Then L of M is equal to R of 1 Fn for all Qf in F. R of ij 0 is equal to A, where Qj belongs to Q by A if I not equal to j, and R of ij1 is equal to A in epsilon sigma, a symbol in sigma, for such that Qia is equal to Qj plus epsilon if I is equal to j, and Rijk is equal to Rijk minus 1 plus Rikk minus 1 Rkk minus 1 star with Rkjk minus 1. So we proved that LM is a regular language by showing that there is a regular expression corresponding to LM by induction. So we will have a basis that Rij0 corresponding to regular expression if I not equal to j, and A plus epsilon if I is equal to j for some A in sigma. So for induction hypothesis, R of ijk minus 1 correspond to expression for any ijk less than equal to n. So we have the induction steps as usual. Now we'll have this, we will find a regular expression for a DFA. So we'll have states Q1, Q2, Q3, Q4, Q5, where Q4 is the starting state and Q5 is the final state. We'll start from Q1, which is transition A, then Q4 to Q2 with A star B, then we connect Q2 to Q3 to Q2 B A star B, then similarly we'll find regular expression for the DFA. And now we'll go to pumping lemma. So this lemma is applicable to check a language whether it's irregular or not. So if L is a regular language, then there exists an integer n greater than positive integer, strictly positive, or it may be 0 but non-negative, or or you may say that there exists a non-negative integer such that for every string x in L with length greater than equal to 10, there are strings u, v and w such that x is equal to u, v, w and v not equal to epsilon, and mod of u, v less than equal to n, and for all k greater than equal to 0, u, v, k, w is also in L. So any language L is not a regular language if for any integer n greater than equal to 0 there is a string x in L such that mod x greater than equal to n. For any string u, v and w, x not equal to u, v, w or v not equal to epsilon, or the condition is given like this. So there exists k which is non-negative so that u, v, k, w is not in L. You have to show it. So any language L is not a regular language if for any integer n greater than equal to 0 there is a string x in L such that mod x greater than equal to n. For any strings u, v and w such that x is equal to u, v, w, v not equal to epsilon and mod u, v less than equal to n. So there is a k which is non-negative so that u, v, k, w is not in L. So using how to use a pumping lemma for a given language L, let n be an integer that is non-negative. So choose a string x in L such that the length of x is greater than equal to n. Now consider all possible ways to chop x into u, v and w such that v not equal to epsilon and mod of u less than equal to n. Now for all possible u, v and w so that there is k which is non-negative such that u, v, k, w is not in L. Then you can conclude that L is not regular. So the question is coming, if you pick a wrong x, your proof will fail. It does not mean that L is regular. So for example, for prove that 0, I and 1 for I not equal to or non-negative is not regular. So string you have to prove it is not regular. Let L be 0, I and 1 I is a non-negative integer. So n be any integer greater than equal to 0. Let x equal to 0 and 1 n. So make sure that x is in L and mod x greater than equal to n. The only possible way to chop x into u, v, w such that v not equal to epsilon and u mod of u, v, that the length of u, v less than equal to n is u is equal to 0 power p, v 0 power q and w is equal to 0 power n minus p minus q and 1 power n. Where 0 less than equal to p less than n and 0 less than q less than equal to n. Now you have to find that there exists k greater than equal to 0 so that u, v, k, w is not in L. So here you can find u, v, k, w by as per our we have chosen u, v, w. So here if k is equal not equal to 1 then n plus q of k minus 1 is not equal to n and u, v, k, w is not in L. Then L is not regular. Now we can prove 0 I, 1 I not equal to not even equal to 0 is not regular. We can prove like this by taking your v and u, v, w. You can find